Hello, the internet. So, another episode of my little Chem Tutor thingy. Again, you're probably watching this on YouTube because this is very impromptu because we had some snow days and whatnot. So I'm just doing it and without an announcement, just so I make sure I get it out there. But yeah, if you're watching this on YouTube, I do these at Google Hangout because it's cheap. And currently, fun fact, I am sharing the Google Hangout space with the Wolfpack podcast and something called How Do You Shut a Bitch Down? So almost decided not to do mine just so I could catch that one. But maybe next time. Hopefully he's a weekly like me. Although I haven't been weekly because there's some, like I said, there's some weather, and when there's weather, schools close and other people in the house, and it helps things go smoothly when I'm at home by myself and there's not people running up and down the hall under the age of 10. But anyway, so we're near the middle of the semester, and this is when we start talking about reactions for General 1. And really, reactions, we start revisiting reactions for General 2. The two do kind of coincide pretty well at about the same time. For General 1, you're into stoichiometry, which is something you're just not going to get away from for a few weeks or semesters, because if you take organic, that stuff never goes away, at least in lab. And in General 2, you're starting to do something called equilibrium, which I always tell people is the stoichiometry of General 2, because once we start it, we're going to keep talking about it for a couple of chapters. All right. So for, like I said, for General 1, we're going to talk a little bit about precipitation reactions. I'm going to, screen share. I was going to say a little bit about net ionics, but I don't want it to go as long as it did last time. That might have been a little too long. I don't know. If you want me to go long, I can. Just let me know. But let's see. In here. All right. So we're talking about precipitation reactions, and a lot of the reactions that are introduced in this chapter follow the same sort of general type of reaction, which are double displacements. So, and most double displacements follow the same generic scheme. You have two compounds that are made up of two parts. Actually, nope, not yet. AB. We'll call them AB and XY. And when they react, they basically do a swap, which gives you something like AY and B. I'm sorry, nope. It doesn't really matter, but yeah, AY and B, XB. I'm trying to keep the same cation anion sort of vibe for this made-up equation, because most reactions that we talk about in this course are reactions between ionic compounds, because they're the simplest ones in chemistry, and really the simplest ones to look at when you're first learning all this chem stuff. And there are a handful that we won't get into that are what we call single displacements, which is where basically you have a compound swapping a partner with an element. So they're again, displacement reactions is basically a partner swap, if you want to be a little perverted. They're swingers, baby. It was a terrible Austin Powers. Wasn't even an Austin Powers joke. Impression. It was awful. But moving on. But let's say, for example, you have the reaction between potassium bromide and silver nitrate. So our two reactions are KBr and silver nitrate to give you, I'm actually jumping ahead a bit. So to figure out our products, again, they're doing a displacement reaction. So these two ionic compounds are made up of two parts, the ions that make them up. Potassium bromide is made up of potassium bromine ion, or bromide ion. Potassium nitrate is made up of potassium ion and nitrate ion. So there's only really one way these two can swap. The cation in one compound is going to hook up with the anion of the other. The cation, and vice versa for the other two ions. So potassium and nitrate is going to hook up to give you potassium nitrate. And silver and bromide are going to hook up to give you silver bromide. And I'm not going to say go through, how we assign phases, because at least not today, because I don't want things to get too long. I'll end up doing the whole chapter, which I don't have time for. But, and plus, people teach how to assign phases a little different. It varies from class to class. But if you go back and assign phases to these guys, both these reactants are going to be aqueous phase. And potassium nitrate should be aqueous, and silver bromide is predicted to be insoluble, so it'll be a solid phase. Remember, the S stands for solid, not insoluble, or not soluble, excuse me. Solid, not soluble. So that should be our reaction, or our equation for this reaction. If I keep the screen still, there we go. I need a bigger tablet. So let's look at another example. Let's look at the reaction between sodium hydroxide and iron 3 chloride. So in this example, we're given the names. So we were taught how to come up with the formulas in an earlier chapter. So sodium is Na, hydroxide is OH minus, and since sodium is in group 1, it would have a +1 charge. So those two should combine to give you a 1-to-1 ratio, sodium hydroxide. Iron 3, because remember the Roman numeral tells you the charge of the iron, is that. Chloride, it's in group 7, which means it should have a -1 charge, or group 7A. So when these two combine, if you remember the crossover method, it should combine to give you a 1-to-3 ratio, FeCl3. Right. So when they do the ion swap, again, the cation in one compound is going to take the anion of the other. So sodium is going to hook up with chloride to give you NaCl. And iron 3 is going to hook up with hydroxide to give you an iron hydroxide. But again, just because there's one hydroxide on the reactant side doesn't mean there's going to be one on the product side, which we kind of saw already. We saw there are 3 chlorides here, 1 here. Kind of like we talked about with the combustion reactions from the previous chapter or previous episode. You can't worry about the number on each side because that's balancing, and you can't worry about balancing until you have the entire equation. So at this point, for predicting the products, don't forget the stuff you learned a couple chapters ago. And these two combine using the crossover method. It should be that. All right, now we can go back and balance, which should be a 3 here and a 3 there. Now you notice this little problem didn't come up in the previous example, because in that example, everybody was +1 or -1. So they were all going to work out to be 1-to-1. But that doesn't happen all the time. So don't forget how to come up with compounds for your products. Learning the stuff that you learned in whatever chapter you guys learned compounds. For me, it's chapter 3 in my class and my book. So yeah, that should be the reaction between those two guys. And actually, yeah, I'll do a net ionics for one. I wasn't, but yeah, I got time. I'm going to do net ionics for at least one of them. because people do get stuck with net ionics. Oh, actually, I got to go back and assign the phases. So again, however you were assigned phases, it's going to vary from class to class. Two reactions is going to be aqueous. Sodium chloride is going to be aqueous. Iron 3 hydroxide is going to be insoluble. So let's see, can I cut and paste this whole thing? That'd be awesome. So yeah, I'll do one of these as a net ionic. Yeah, oh, whoops. Oh, I know why I did that, because of, oh, never mind. Right. So let's say you want to come up with a net ionic of this reaction. So with net ionics, at this point, this early on in, for most classes, the trick is, if it's aqueous, you're going to show it as dissociated ions, because most aqueous compounds you're looking at this early in Gen Chem are ionic, and remember, ionic compounds dissolve by dissociation. So sodium hydroxide is going to dissociate into sodium ion and hydroxide ion. So if it's aqueous, show it as separate ions, or basically you break up compounds that are aqueous. So those 3 sodium hydroxides are going to break up to give you sodium ion and hydroxide ion. Now, you don't have to keep it balanced in most cases, but I like to keep it balanced all the way through. So 3 NaOHs give you 3 NAs and 3 OHs. All right, iron 3 chloride is aqueous, which means it's going to dissociate into iron 3 and those 3 chlorides. The 3 sodium chlorides are going to break up to give you 3 sodium ions and 3 chloride ions. All right, the final product, iron 3 hydroxide, is a solid. So remember, if it's a solid, a liquid, or a gas, you don't break it up, because it's not dissolved. It's a solid, it's a precipitate, it's not dissolved. It's a solid that's either sank to the bottom of your beaker, or it might be fine enough particles where it's floating around, but it's not dissolved. So you're only showing the aqueous compounds as dissociated because they're the only ones that are dissociated, the only ones that are dissolved. But the short of it is that if it's a solid, liquid, or gas, you leave it alone. And at this point, basically, if it's aqueous, you break up into ions. That's not true all the time, but this early on is probably true for your classes, unless your class is talking about weak and strong acids, which in that case, there might be a little caveat to what I just said. But if you're taking my class, I don't talk about that till Gen 2. So once you have it completely broken up, you look to see if you can find the spectator ions, which are the ones that are exactly the same on both sides of the equation. For example, you got 3 sodiums on the left, you have 3 sodiums on the right. So those are spectators, right? They haven't changed during the course of the reaction. Hydroxide, its identity's changed because you've gone from aqueous ions to a solid product. And all of these are aqueous. I was just lazy and didn't write the phases every time. Yeah, these are hydroxides in 2 different environments. So it's undergone a chemical change. Aqueous ion to a solid product. Same thing with iron 3. Chloride, though, you have 3 chlorides on the left, 3 on the right. So yeah, those are spectators. So if you simplify this equation, kind of like you simplify an algebraic equation, you remove the stuff that's the same on both sides. What's left is your net ionic, which would be 3 hydroxides and 1 iron 3 ion to give you iron 3 hydroxide, which is basically what a net ionic is showing you, is that It's showing you the actual reaction that's taking place. And the actual reaction taking place is the hydroxide ions and the iron ions are combining to give you that precipitate, that solid. Sodium and chlorine, they're not reacting. You have sodium ions floating around on the reactant side. On the product side, there's still sodium ions just floating around as aqueous ions. So they haven't undergone a chemical change. Some people will ask, does it have to be the same number on each side? No, most of the time it is, but there are some examples where some of the ions are reacting and some of them aren't. So you kind of got to mix. An ion can be a mix of being a spectator and a non-spectator. But most of the time, if you keep it, that'll happen. But if it doesn't, then that's okay too. Right. So that's precipitation and double displacement reactions. And like I said, most of the reactions you guys talk about in the chapter on aqueous chemistry, aqueous reactions, they're some type of displacement. Most of them are double displacements. There might be one or two that are single displacements, but they're basically just ion swap, kind of like we saw for those previous two examples. But don't let that mess you up on combustion reactions from what was probably the previous chapter, because those aren't any kind of displacements. And those are just solely based on what elements are present in the compound reacting with oxygen. Carbon is going to give you CO2, hydrogen is going to give you water, and so on. Those aren't displacement reactions. Again, those are elements combined with oxygen to give you their main oxide, which is a little different. So as you get into these aqueous reactions, don't let that throw you from the stuff you were taught in the previous chapter. Excuse me, water. All right, so that's general 1. Moving on to the general 2, guys. Like I said, general 2, you guys are going to start talking about equilibrium. And I figured one topic that'd be good that I don't think I talked about in my previous set of videos, Gen Chem concepts. And for this first series of videos that I'm doing, semester, whatever you want to call the S in the title of the video, I'm trying to mainly hit on topics that I didn't cover in those, although eventually I'll come back around because I don't always teach those the same way that I did however many years that was. 8? Shit, was it 8 years? I don't know. I'm afraid to look now. It was a while ago. It was back when YouTube wasn't really an option. Here's how old the general chem concept videos are that are linked on this YouTube channel. Originally, those were given out to students on CD-ROMs. Remember those? So yeah, they'd give me a blank CD-ROM. I'd burn them on the CD, and then I'd give them back to them for free. But then YouTube started, and I thought, hey, I could just load them there and not worry about it. But that's just maybe. So moving on to General 2. Like I said, General 2, one topic it kind of gets people a little loopy early on is this thing called the reaction quotient. Quotient. I think it's an E. I can't spell today. Symbolized with the letter Q. And before we talk about that, just to remind you how the equilibrium constant works. Remember, for any equilibrium, oops, not AB. For any generic equilibrium reaction, you know, A and B give you C and D. It's products. D's are the uppercase are the chemicals, lowercase are the coefficients. So any reactions like this where things are in the aqueous phase, or if everybody's in the gas phase, solids or liquids changes what I said a little bit, as you've probably been taught already. But for any reaction like this, you have this thing called the equilibrium constant, which is basically a ratio of product to reactant. It's basically, most of the time we look at the concentration, which is what the C stands for here. Some people just use an EQ. I like to use a C because sometimes you do it with pressure, which is Kp. But it's just, however you do it, it's just a ratio of product to reactant where each concentration or pressure for Kp is raised to a power equal to its coefficient. But if you're not at equilibrium, in other words, these concentrations are anything but the concentrations to give you this magical constant K. You have this thing called a reaction quotient, and it's the ratio of each product over each reactant, and each one raised to a power equal to its coefficient. And students will look at that and say, hey, they're the exact same equation. Yeah, that's kind of the point. The only difference is that for K, these are the concentrations when this reaction hits equilibrium. Oops, put another arrow. When Q is basically any other time. Any other concentrations that aren't that magic ratio to give you K. Right. When Q equals K, then that's when your system has achieved equilibrium. At any other time, the chemical system is going to try to achieve equilibrium, and it does it by doing this thing called shifting. If you end up with a Q that's, if your concentrations give you a Q that's smaller than that reaction's K, then it's going to do a thing called shift to the right. Because remember, at equilibrium, both reactions are occurring at the same rate. A shift to the right means the forward reaction, reactant product, is going to pick up the pace a bit to make more product than the reverse reaction is making reactant. So basically picking up speeding this reaction up until you have enough product where this reaction or this ratio meets the conditions for equilibrium. If Q is greater than K, then you do what we call a shift to the left. Same but opposite. Now the reverse reaction is going to go a little bit faster, pick up the pace. So, because to convert, to pick up the, increase the amount of reactants that are present. So again, you meet the criteria for whatever Kc needs to be, whatever that ratio needs to be. And something I use to kind of help keep the direction straight is I like to think of a number line. I think they still teach number lines in whenever you were taught number lines, what, junior high, elementary school, I don't know. Whenever you're taught number lines. But at the point where Q equals K, that's equilibrium. If Q is a bigger number than K, then it's going to go to the left. If Q is a smaller number than the value of K, it's going to shift to the right to achieve this, again, state where both of those values are the same number. So, for example, let's look at the reaction between made-up reactants A and B. To give you made-up product C. And again, it's equilibrium. We'll put in the other arrow. And let's say the equilibrium constant with respect to concentration for whatever this reaction is 0.82. All right, remember there are no units for, well, there are units, we just ignore them because it varies from reactant to reactant. So they really don't serve any purpose for us. So we usually ignore rate constants and equilibrium constants units for just keep things simple, because again, it varies. But let's say the concentrations are currently, let's say you start off with concentrations that are 2 molar A, 1 molar B, and 0.5 molar C. So, Ian, you started out with these concentrations, you mixed them all together. I guess to be complete, I got to put in phases. We'll put in gas phases here. So these may be the right concentrations for equilibrium. Probably not, especially if you just pull these numbers out of your butt like I just did, or wherever you pull out numbers. So to see if these are the equilibrium concentrations, and if they're not, what needs to happen to achieve equilibrium, you plug it into your expression for Q. So in this case, it would be C squared over A squared times B. And plugging in our concentrations that were given, it'd be 0.5 squared, 2 squad, and 1. And hopefully I didn't screw up this calculation. It should be 0.063. So the Q does not equal K, so it's not at equilibrium. Now, what's going to happen? What has to happen for this thing to achieve equilibrium? Well, it looks like the Q is smaller than K. So again, when Q is smaller than K, it's going to have to shift to the right to achieve equilibrium. Again, the forward reaction is going to have to pick up the pace, move a little bit quicker to increase the amount of C at any given time until you get that magic ratio that makes the equilibrium constant 0.82. And once you achieve this magic ratio, then you get equilibrium, and both directions will occur at the same rate. So another way to kind of keep the idea of shifting right and left straight is I like to have students picture a little two-pan balance. I can get my camera up here. A little two-pan balance. If you're a Metallica fan, think of the album cover "Injustice for All." Lady Justice if you're just a legal fan. All right. But at equilibrium, both my hands are so big right now. Both hands, both you get it's in balance. All right. If your Q is bigger than K, that means your ratio is too top heavy. You got too much product, so that causes the to be if you're too product heavy, you got to take some of the product and move it over to the reactant side until it starts to balance out. If Q is smaller than K, that means you're too bottom heavy. And you have too much reactant. This is harder to do than I thought it was going to be because my camera's too high. So you got to pick up the pace where you're moving some of your reactants over to the product side until it balances out again. Now the flaw in that little visual aid, besides it makes me look like I'm a mime juggling, is that you think balance, you think equal amounts. Again, equilibrium doesn't mean equal amounts, it means equal rates. And also too, when the shift occurs, whichever one's picking up the pace, the reverse reaction is occurring at the same. It's also occurring, it's just whichever direction the shift needs to occur, that one has to go faster than the other one. Again, until you get things balanced out to give you whatever the concentrations need to be to achieve the equilibrium constant. So that's a quick and dirty lecture on the reaction quotient. And I think time was a lot better this time. I don't know. I'm still playing around with time. A lot of people will say for this video stuff, if you go to QMed conferences, and I do from time to time, they say that they should be short. Last one was really long. I don't know. Sometimes I think shorts might be too short. You know, it's like when people talk about how long video games need to be. You know, what's too long and what's too short. It's however long it needs to be. But since I'm probably going to try to do a 2 for today, just so I can get caught up, because I'm hoping to do 16 this semester. That's short enough. All right. So that's it for today. See you guys next time. Bye.